today's lesson is the third of 3 lessons about X-rays. So we met last week how X-rays are produced in the scanner and then how they interact with the human body. We aren't going to talk very much, well, at all actually now, about how the X-rays are detected and the electronics that goes with that. We'll talk about it a little bit in the context of some of the other technologies that we're going to come on to on Wednesday. But today what we're going to do is extend X-rays into something I'm sure you've heard of, which is called a CAT scan or a CT scan. Both phrases are in common use. So today's lesson, computerized axial tomography, which is quite a cool name. In 27.3 of the textbook, and I'll be asking you to have a read of that at the end of the lesson. Okay, so if you don't know, if you've never seen one, that's what a CT scanner looks like, or a CAT scanner. It's not quite the huge machine that an MRI machine is, if you've seen one of those. It's also a donut. The 2 machines have that in common, and the patient goes through the hole in the middle, but the CT scanners are a lot more compact. It looks quite neat and tidy and almost simplistic from the outside, but if you have a look on the inside, you can see all of the engineering know-how that's gone into making that thing, with all of those electronics and other components scattered around the patient. So we're going to have a little look today about what a CT scanner does and a little bit about how it works. Okay, so axial means that the scanner scans along the human body's axis, so from head to foot, or the other way around, from foot to head, but it means that it takes scans along the human body, so that's the axial bit. And then tomography, breaking that word down, the first part of that word refers to slices, so it's kind of making thin pictures, thin slices of the human body. So as the scanner makes its way from head to toe, it effectively chops the human body up into wafer-thin slices. You can see some slices through the head there, and each one of those slices will be very, very thin, and then it builds them all up into a full image of whichever area of the human body is being looked at. Tomography kind of refers to flat planes. I don't mean planes in the sky. A plane's a mathematical thing. It means a flat surface. So we're mapping the human body by making images of flat surfaces, slices through the human body from top to bottom. Okay, so here is a experiment. I'm going to try to show you a video, which is going to mean that I'm downloading it at the same time as I'm uploading it, which may or may not work. So we'll see. If it doesn't work so well for you, it'll work fine for me, but if it doesn't work fine for you, with you being able to see it, if it's jerky or anything, it's just a couple of minutes long, and it's embedded in the PowerPoint, which is on Google Classroom, so you can play it back yourself later. Like I say, if it's not working, it's only about 2 minutes long. Let me know if you can't hear sound.
A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in 2-dimensional form or stacked together to generate a 3-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments.
Okay, so there are a couple of really key differences between the operation of the CT scan and the X-ray, even though they're both based upon the same source of X-rays, which is releasing X-rays, and the same detector technology that's capturing those X-rays as they come through the other side of the patient. If you look at the diagram that's on the screen now, you can hopefully see that it's kind of a fan-shaped beam of X-rays that comes out, whereas in a conventional X-ray, it would be a cone of X-rays that comes out. It's almost as if the three-dimensional cone of a regular X-ray, which produces a two-dimensional flat image, has been squashed in one direction, so that effectively it's almost a one-dimensional beam of X-rays that comes in. It's going to take a picture of the width of the patient, but only a millimeter or so wide. The thickest it would ever be is about 5 millimeters, and quite often it's sub-millimeter in thickness. Also, when we look at X-rays, usually it's a single X-ray from one direction. And so we see a two-dimensional image that's effectively a shadow of a two-dimensional flattening of the patient. But in this case, what we're going to be doing is taking X-rays from multiple directions. The X-ray scanner and source spins around the patient and takes multiple images, usually about 1,000 per rotation, actually. The X-ray source is left on continuously, and the detector just effectively opens and shuts its shutter, by analogy, taking around about 1,000 X-rays per rotation. And those X-rays are very, very thin one-dimensional pictures, not a two-dimensional picture. And then those say 1 millimeter thick images taken from all different angles around the patient need to be put back together again by a computer to make a two-dimensional image, but not like a chest X-ray is a two-dimensional image in that you are looking at the chest of the patient and there is the up and down direction and the left and right direction. And when that's mapped onto an X-ray, you have, the part of the chest that's down by the stomach, and the part of the chest that's up by the throat, and the part that's by the left arm, and the part that's by the right arm. It's not that two-dimensional image that's going to be produced. Instead, it's a little bit more like you've sliced the patient open from the front of their chest to their spine, and you've taken the head and shoulders off, and you're looking down on a slice across the patient. So very, very different two-dimensional image that the CT scan produces. Just another quick video to show you how it manages to do 1,000 images per second. I think a lot of people tend to think that the X-ray scanner might rotate quite slowly around the patient. This is a cross-section of it being tested. So you can see it spins very, very fast. This isn't a gentle machine. And when you're near one, when it's on, you do just hear that gentle whirring sound. But I think it's hidden from the patient just how much metal is spinning around them at any one time. Oops. Okay. So in a conventional X-ray, if you look at the image on the side of the screen there, the conventional X-ray would show you detail within the black shadow region. So it would be an up, down, left, right image that's taken by a conventional X-ray. But a CT scan only takes the part that's inside that red rectangle that I've drawn on there. So it's a slice in a different direction, a horizontal slice in this orientation. And it takes that picture from multiple angles. The diagram is showing you from 2 angles, from the front of the person and from the person's left-hand side. And you can see that the shape of the shadow within the black rectangle is different from the 2 sides. And what the computer effectively has to ask is, it's got 1,000 shadows from 1,000 different angles, and the computer has to work out what shape the 3-dimensional object has to be so that it casts those 1,000 shadows from those 1,000 angles. So you can see where the C in CT scan comes from. This wasn't possible until about 15 years ago, when computer chips got fast enough that they could do this in a realistic amount of time. And these days they do them pretty much on the fly. So a great deal of computer processing, taking the imagery from the scanner and asking the question, what shape was the 3-dimensional object that produced these 1,000 shadows? And then when it's done that, it knits it together into just one of these pictures. So this picture here would be the result of all that computer processing, in which the scanner has looked from the top and the side and the bottom and this side and this angle and this angle and this angle, and all of those shadows have been put together to produce that 2-dimensional slice through the patient. And then what we do is the bed arrangement that the patient is lying on, we then move that bed through the scanner. So as the patient moves through the scanner, in one rotation of that very fast moving gantry that you just saw, the patient might nudge forward 1 millimeter. And so by the time 360 degrees has taken place and it starts the second rotation, there's a different millimeter of patient axially from head to toe underneath the beam of the X-rays. So the patient would then be moved through the scanner for as far as the part of their body needs to move in order to have that bit imaged. So it's unusual for a patient to have a full body CT scan. Usually the doctor is trying to diagnose something about a particular area of the patient, be it their brain or their lungs or their kidneys or whichever part of the body. So it's not normal for all of the patient to go through the machine. And in actual fact, a CT scan might last under a minute because it might only be a small part of the patient that is being imaged. Okay, so if you look down at this bottom left, this is just as the patient's head is leaving the scanner. So if you look at the pictures this way, you're effectively, it's a bit gory, but it's almost like pushing the patient through a bacon slicer and slicing off the top millimeter of their head to reveal the very, very tip of their skull, and then slice a bit more and slice a bit more. You can see this is the bone that we're going through. And then we get to brain. And so this is slices and slices and slices of brain as we head through the patient from the tip of their head down through the middle of their head. You can see detail inside the structure of the brain here. And then you can just about to start to see the cavities within the front of the skull. Here's the eyes starting to appear, a little bit of the nasal cavity. Here's the eyeballs. As we pass through, you can see the nose gets bigger and bigger and bigger. And then we pass through the eyeballs now. So I guess these are sinus cavities. And then this was as much as needed to be imaged for this patient. We've run out of brain by this point, and you can just see that there's, I guess, the top of the brainstem heading off down the spine. So it is amazing, the technology. Those are all 2-dimensional images. You can string them together, though, stack them up so that when you just roll your mouse wheel, you can zoom in and out of the patient. So I've got a video of that as well. Frustratingly, I couldn't find a high-resolution video. So this is a low-resolution video, which is really annoying. See if you can find a high-resolution one later on and send me a link if you find one. But here's a kind of roll through the body. So we're at the head, and there's the shoulders on the left-hand side. And then we're into the main thorax. There's the lungs. Will be around the hips, I guess, around about now. And oh, that must be hips. There they are. And then those are the top of the hip bones. And then we're disappearing down into the legs. You can see the bones. Yeah, if you can find a higher res picture, that'd be amazing. I've seen one once, but I couldn't find it. Okay. Things you should know about CAT scans versus conventional X-rays. Okay, so the technology, because it has a computer behind it, interpreting the images and coding them with false colors so that different parts stand out. A CAT scan is incredibly high resolution, much more detailed than a regular X-ray would be, mainly because it has been taking the pictures from all those different angles, and so it can assess the shadows from much more greater angles and interpret them much more finely. Also, I think these X-ray scanners, I think they have binocular vision. I think there's actually 2 X-ray scanners that are shooting the X-rays across from minutely different angles. And so, like human vision can perceive depth better by using a binocular vision system, I think the CT scanner works in the same way. And so much more likely to produce images that have had their fuzziness removed from the edges of all of the tissues that are being imaged. You can also use contrast media with CT scans, just like conventional X-rays, although it's not required because the resolution is just higher anyway, but you can make pristine images using contrast media as well. But it's important that you realize that the X-ray scanner is on continuously for the entire time that the patient is in the scanner. So for a conventional X-ray, it's a click, and the X-rays are released for a fraction of a second, and the patient receives a fraction of a second's worth of exposure. But it is on continuously with the CT scanner as the X-ray emitter goes round and round and round the patient. And it might go round and round the patient 60 to 100 times, depending on the size of the scan. So the patient does receive a much larger dose of ionizing radiation. And for that reason, you would need a medical justification for a CT scan. You would never be putting a CT scan just for a laugh, just to image the inside of your body so you could go put a picture on your wall. You are receiving quite a large dose of ionizing radiation, and that would be justified by the doctor making the call that they do suspect that you do have something quite serious wrong with you. For instance, maybe you've been in a car crash and you have a headache, and your concussion isn't clearing up quite as quickly as they would like, and maybe they're worried that you have I don't know, a bleed under your skull, and that would be serious if not dealt with, life-threatening. And so the minor damage that you would receive from the ionizing radiation from the CAT scan would be more than offset by diagnosing and treating the much more serious underlying life-threatening condition. That said, there are some lines that doctors will rarely cross. So, for instance, pregnant women are highly unlikely to be given an X-ray. An X-ray actually, but they might if it was away from the abdomen and they placed a lead apron over the abdomen to protect the fetus, but highly unlikely to receive a CAT scan because the amount of ionizing radiation that the fetus would receive would be very damaging to the fetus. You remember that within a fetus, the cells are dividing very, very, very rapidly. And if one of those cells were to be damaged by the ionizing radiation, then it would that damaged cell would divide very, very, very rapidly and produce a malformed part of the fetus. So CT scans are not recommended unless there is a real risk of the patient dying imminently. Pregnant ladies would not be put in a CT scanner. But other than that, fair game. And although I've only been speaking for 20 minutes or so, that's actually it for CT scans. I don't really want to use the rest of this lesson to push on to a new technology, because we've done 2.5 lessons on X-rays now. And the next technologies that we'll move on to on Wednesday are completely different, nothing to do with X-rays. So I'd rather stop there at half a lesson and leave it there, and leave you with some work to do instead. So if any of those videos didn't work for you, please watch them back, or watch them back again anyway. Do some own Google imaging searching for CT scan images. There's really impressive ones out there, really, really cool things that have been imaged inside the body. Lots of false color imaging so that different structures inside the body stand out. You might want to, if you're interested in medicine or diagnostic medicine, you might want to have a look at what CT scans are best used for diagnosing what types of conditions. Although that's not examinable on your physics A level. If you find yourself in a medical or medical science university interview next year, it'd be good to be able to talk about these kind of things. But specifically, what I would like you to do, please, maybe for the rest of this hour, is have a read through 27.3 in the textbook. Make any basic summary notes that you need to, although, to be honest, there isn't very much to CAT scans, as I've just shown you. And then have a go at some of those questions that are at the summary page at the end of the chapter.